Good day. For those of you who don't know me, my name is Douglas Harder, and in this topic we're going to discuss phasors. So basically we're going to be looking at the sum of sinusoidal functions, all of which have the same frequency. We're going to see that the trigonometry involved with this is quite complex, and then we will see that we can simplify this operation by transforming to complex numbers, or phasors, and therefore we will have a phasor representation of these sinusoids. We will then convert this trigonometric addition into phasor or complex number addition. We will see why this phasor representation works. We'll then carry on and look at phasor multiplication, phasor inverses, which we will then use and apply to linear circuits with alternating current. So let's consider an arbitrary sinusoid. It will have some period t. The frequency is 1 over the period, and the angular frequency is 2 pi times the frequency, the angular frequency being in radians. It's always possible to write such a sinusoid in terms of nu cos of omega t, where nu is the amplitude and with a phase shift phi. Now, the cosine function is periodic, and therefore we can actually restrict phi to be a value between negative pi and positive pi radians. Engineers, however, throw a twist into this. The angular frequency is always in terms of radians, but the phase shift is usually written in terms of degrees. So therefore the phase shift will be restricted to values between negative 180 and 180 degrees. So for example, we may be looking at sinusoids of the form v cos of 377t plus 45 degrees, right, this is in radians, or v cos sine of 377t minus 90 degrees. Now, a positive phase shift means that a function is leading in time. So for example, negative sine is cosine of t plus 90 degrees. Now if we're looking at, as time advances, we notice that negative sine peaks before the cosine function. So therefore the sine function is leading the cosine function in time. The same thing happens if we look at cos of 377t and cos of 377t with a phase shift of plus 45 degrees. The blue function, the leading function, peaks first, and only after the blue function peaks does cosine of 377t peak. A negative phase shift causes a lag. So for example, sine of t is cos of t minus 90 degrees. So as time moves forward, we notice that cosine peaks before sine. Well, it doesn't matter whether or not you're using sine or cosine of t minus 90, or cosine of 377t and cos of 377t minus 90 degrees. Cosine peaks first, then the function, or this sinusoid, with a phase shift of negative 90 peaks. Now, if the phase shift is exactly 180, that means they're out of phase. Negative cosine is out of phase with cosine. Same thing with cosine of 377t, it is out of phase with cosine of 377 degrees t plus 180 degrees. Now, suppose that we want to add a whole bunch of sinusoids, all of which have the same angular frequency, but where they may have different amplitudes and different phase shifts. For example, here's a sum of 5 trigonometric functions, all with different amplitudes and phase shifts. Now, it might not be immediately obvious, but because the angular frequency is the same, the result will be a sinusoid with some unknown amplitude, but with the same frequency, 377t, plus some unknown phase shift phi. In fact, in Maple, if you plot the 5 functions, you can also plot the sum of these functions, and you get 14.81 cos of 377t plus an angle or phase shift of 3.36 degrees. Now we're going to show that the sum of two sinusoidal functions with the same angular frequency, but with different amplitudes and different phase shift, still results in a sinusoid with the same frequency. Our derivation is not going to use trigonometry any more complex than what you learned in high school. Later, however, we're going to see how complex exponentials can simplify all of this significantly. But, going back to trig, 3 cos omega t plus 9 root 2 cos omega t plus 45 degrees. Using the cosine sum formula, I can expand this term to get that this is equal to this expression, and that's 9 cos omega t minus 9 sine omega t, and I can add these two terms when I add the two together. So summing these two gives me that sum of a cosine and sine, both with argument omega t. Now I want to write this in terms of this formula, and so all I will do is, again, apply the cosine sum formula, and notice that I have cosine omega t and sine omega t here. Well, if that's true, then nu cos phi must equal to 12, and negative nu sine phi must equal to 9. So therefore I have two equations in two unknowns. However, they're nonlinear equations. But still, given these two, don't give up hope. I can square both sides and add them. Well, the sum of the squares of the right-hand side is just 225. If I square the left-hand side and add them, I get a common factor of nu squared, and, oh wait a second, cos squared plus sine squared is 1. So I get nu squared is equal to 225. Take the square root of both sides, nu is equal to 15. Let's take these two formulas again. Well, let's take the ratio of them. We'll take the ratio of the second over the first. The amplitudes cancel out, and I'm left with tan of phi is equal to 9 over 12, or 0.75. Well, therefore phi is arctan of 0.75, and therefore phi is equal to approximately 36.87 degrees. So therefore it follows that the sum of these two sinusoids with the same angular frequency, but with different phase shifts and different amplitudes, does result in a sinusoid with the same angular frequency. In fact, it doesn't matter what the angular frequency is, omega t. If omega is equal to 2, I can plot both of these, and I can plot their sum, or I can plot this, and I get the same result. Or if I let omega is equal to 5, these are the two functions, I can add them together, and I get this function here, which is equal to that. Now, this is proof with a specific example. However, if you wish, you can also prove this in an arbitrary case. Now, what happens if we want to add 5 or 6 sinusoids? Well, we do this pairwise. Add the first two, that gives us a sinusoid still with frequency omega t. Add that to the third sinusoid to get a new frequency, a new trigonometric sinusoid. Add that to the fourth one, keep on adding pairwise until you get a result. Now this is complex at best, calculating all of these, so it's a lot easier, or we're going to simplify this problem by going into the complex domain. Remember that any complex number is comprised of a real part plus an imaginary part. However, I can also think of this complex number as an object with a magnitude, nu, and with an angle from the positive real axis, phi. And so every single complex number can either be represented as a plus bj, or as some magnitude with an appropriate angle. That is our phasor, and assuming that our angular frequency is fixed, I'm just going to associate nu cos of omega t plus phi with the complex phasor phi phase phi. New phase phi, sorry. Nu is the length, phi is the angle. So there is my complex number. Now, normally when we're trying to calculate the sum of trigonometric functions, we would have to do the operation we considered before. However, what we're going to see is that we can actually transform this function. For every single sinusoid here, I'm going to consider its representation phi, phase, nu sub k, phase, phi sub k. And then over here, rather than adding these trig functions, I'm just going to add these complex numbers. Well, complex numbers addition is quite easy. Out of this complex number addition, I'm going to get another complex number, nu phase phi. But remember, with my association, nu phase phi is associated with a sinusoid, nu cosine omega t, with a phase shift of phi. So these two are related, so I can go back. Now the question is that nu that I get there as summing these complex numbers going to be the same amplitude that I get if I sum these trigonometric functions? We're going to see that that's actually true. And it's actually very straightforward to see once you're looking at complex exponentials. So what we're going to do is we're going to transform a trigonometric problem into a different domain, the complex domain, perform a very simple operation in the complex domain, and then transform back into a trigonometric function, or a sinusoid. How are we going to do this? Well, once again, let's remember that nu phase phi is just Eulers identity. It's nu e to the j phi, and that's just nu times cos of phi plus j times nu times sine of phi. So a real part and an imaginary part. So therefore, if I'm adding a whole bunch of phasors, I'm just adding the magnitudes times cosines of the angles plus j times the magnitude times the sines of the angles. Now, from our motivating example, we had 3 cos omega t and 9 root 2 cos omega t with a phase shift of 45. Well, that's 3 phase 0 and 9 root 2 phase 45. These are those two complex numbers. Now, if I add these two complex numbers, I get a complex number that has slightly longer length than 9 root 2 with a slightly more shallow depth, or 15 phase 36.87. This complex number, or this phasor, is associated with the trigonometric function 15 cos omega t with a shift of 36.87 degrees. Notice that there is a one-to-one relationship between every single complex number and every single sinusoid with a different amplitude and different phase shift. If I have a different amplitude, I will get a different complex number. If I change either component of the complex number, I will get a different sinusoid. So it's a one-to-one mapping between phasors and trigonometric functions of the form amplitude times cos of omega t with a phase shift. Let's look at our sum of 5 sinusoids. So this first one is 3 phase 75. The second one is 10 phase 50. Well, going into the phasor domain, we are now just adding these 5 complex numbers. Straightforward enough. We get 14.78 plus 0.87j. That is represented by the phasor 14.81, phase 3.36 degrees. The associated trigonometric function has an amplitude of 14.81 with a phase shift of 3 3.36. So here we have a couple graphs. This first graph shows the 5 complex numbers. We can add the 5 complex numbers to get this result. This result is the phasor 14.81 phase 3.36. On top, I plot the 5 functions, and the bottom I plot either their sum or this function, and they are, of course, identical. Now, to see why this works, we have to go to complex exponentials again. Now, rather than having nu e to the j phi, I'm going to add an omega t into there, into the exponent, or a j omega t. So now I have nu e to the j all times omega t plus phi. Well, what does that represent? Well, Euler's formula, that's nu cos of omega t plus phi plus j times nu sine of omega t plus phi. So essentially, the cosines that we've been looking at are simply the real part of this complex exponential. So remember that any exponential with a fixed multiplier with an purely imaginary real part, exponent, as t changes, we're simply spiraling in the complex plane. If we take the projection onto the real axis, in this case we just get 14.81 cosine of 377t plus that phase shift. If we project down into the imaginary plane, we get 14.81 sine of 377t plus a phase shift of 3.36 degrees. Now, notice that if I sum 2 complex exponentials of this form, what happens? Well, here I have the exponent e raised to a sum. Well, the power of a sum is just the product of the powers. So each of these can be converted into e to the j omega t times e to the j phi 1 in the first case, and in the second case e to the j omega t times e to the j phi 2. Oh, wait a second. I can factor out that term of e to the j omega t. It's out there. So what's left? Nu 1 e to the j phi 1. That's our first phasor. Nu 2 e to the j phi 2 is the second phasor. Nu 2 phase phi 2. So essentially, calculating this sum of 2 complex exponentials is reduced to calculating a phasor addition. This component remains unchanged. Now, recall that the real part of a sum of complex numbers is the sum of the real parts. So, we were trying to calculate the sum of these 2 trigonometric functions. Well, this is the real part of this complex exponential. This is the real part of this complex exponential. I'll break them apart. The sum of 2 real parts is just the real part of the sum. And from here, we saw that this sum is nothing more than a phasor addition times e to the j omega t. So to calculate this, all I need to do is calculate that phasor addition. The e to the j omega t remains unchanged. So previously we used trigonometry to show that the sum of 2 sinusoids was in fact, with the same frequency, was something that had the same frequency. Now we're using complex exponentials. So we see that the real part of this plus the real part of that is the real part of e to the j omega t with the sum of the 2 phasors. the j omega t remains unchanged throughout. But that is why we require that the frequency is unchanged. So now we're just going to go on to phasor multiplication and phasor inverses, and then we will use this to solve voltages across a few very simple linear circuits in series and in parallel. If I want to take a product of two phasors, R1 phase 1, phi1, R2 phase phi2, I take the product of the magnitudes and I add the angles. So for example, 5 phase 45 times 2 phase negative 60, multiply the magnitudes, add the angles, and I get 10 phase negative 15. This generalizes to arbitrary products. If I want to take the product of n objects, that's just the product of the n magnitudes with a phase, the sum of the angles. Now the inverse of r phase phi is just 1 over r phase negative phi. For example, the inverse of 5 phase 45 degrees inversed is 1 over 5, or 0.2, phase negative 45. And why is this true? Well, we can see that it's true at least by taking the product of the phasor, r phase phi, multiplied by its inverse. We multiply the magnitudes, that's equal to 1. We add the angles, phi plus negative phi is 0. Well, 1 phase 0 is the real number 1. So now let's apply this to linear circuits. We're going to be dealing with alternating current, and if we're dealing with alternating current, then we can actually interpret all of this in terms of complex impedances. So whether or not we have a resistor, inductor, or capacitor, they all have a complex impedance when we are dealing with with alternating current. So generalized resistance, complex resistance, is called impedance. So it's resistance plus a reactance. Generalized complex conductance is admittance, and it is conductance plus an imaginary susceptance. Now Ohm's law was voltage is equal to current times resistance. Well, in this case, for alternating current, it remains unchanged. Voltage is equal to current times the complex resistance, or the complex impedance. Now, the impedance of each of the linear circuits actually does act like a phasor. So if we have an inductor with inductance L, its impedance to a linear circuit, to an alternating current is j omega L, or just omega L times 90 degrees. The higher the frequency, the more it impedes the alternating current. Resistance is not affected by the current. So resistance is just, the impedance of a resistor is just the resistance phase 0. The impedance of a capacitor is 1 over j omega c, where c is the capacitance of that capacitor, and 1 over j omega c is just 1 over omega c phase negative 90. So notice that the higher the frequency, the less a capacitor impedes or resists an alternating current. So again, capacitance and inductance are frequency dependent. Now we can use this to determine the voltage across a linear circuit by using the formula V is equal to Iz. Now let's say we have these three circuit elements in series. A resistor of 2 ohms, inductor with 50 millifarads, and a capacitor with 750 millifarads. 50 millihenries. The total impedance is the sum of the impedance. We're trying to get across here, so it's the impedance of each of the circuit elements added together. Well, 2 phase 0 plus omega 0.05 phase 90 plus 1 over 0.75 omega phase negative 90 is a complex number. So if omega is equal to 1, then we can just substitute 1 into both locations, calculate this complex number, and we get 2.376 phase negative 32.69. Let's say that with this impedance we have a complex current, or a current, that is 10 cosine t amperes. Well, voltage across here then can be calculated by just taking the product of this phasor and the associated phasor 10 phase 0 of the current. 10 phase 0 times that is just 10 times the magnitude, so we get 22.76 phase negative 32.69. So therefore the voltage is peaking at 23.76, and it has a phase shift of negative 32.69. That means it's lagging behind. The current peaks, and then after it, the voltage peaks. Yes, the voltage peaks. Now, let's say we have a different current, 377T instead of 1T. Well, let's recall that the impedance of the capacitor was 2 phase 0. The impedance of the inductor is omega 0.05 phase 90, and the impedance of this capacitor is 1 over omega 0.75 phase negative 90. So now we have to substitute 375 into each of those locations and calculate it, and we get 18.95 phase 83.94. So therefore, if we want to calculate the voltage across this circuit with this current passing through it, V is equal to IZ, essentially we're multiplying the magnitude by 10, and so therefore we get 189.5 phase 83.94. With a higher frequency, the inductor is impeding that current, that very quickly alternating current, and therefore this is producing the significant effect, as you can see here, phase 90. So this is positive, this is the dominant effect of this circuit with such a high frequency. So therefore the voltage peaks at 189.5 and it has a lead of 83.94 degrees. Now let's consider these same three circuit elements, but let's consider them in parallel. Now, how does this work? Well, because they're in parallel, let's deal with how much can get through. Well, however much can be admitted through, the admittance, is the sum of what can be admitted through the first one, plus the sum of what can be admitted through the second one, plus the sum of what can be admitted through the third one. Well, the admittance of each of these is just 1 over their impedance, and so the admittance Y of this circuit is just the sum of the three admittances of each of those, or the sum of the reciprocals of the impedances. I can calculate that value. If omega is equal to 1, I can substitute omega is equal to 1 to both of those, calculate the admittance, and the impedance is 1 over that. So I can calculate the inverse of this. So it's the inverse of the magnitude and with a sign change on the phase shift. So there is my impedance of this circuit element, and if I now have a current of 10 cos t passing through that circuit, I can now calculate the voltage across it. V equals Iz. Well, essentially, again, multiply the magnitude by 10, I get 0.5276 phase 83.94. So the voltage is leading the current by 83 or approximately 84 degrees. Let's say I instead have 377 as my frequency. Well, then again, I have to substitute 377 into my impedances, calculate the admittances, take the sum of the admittances. That gives me my Y. I can now calculate the impedance by taking the reciprocal. Well, the reciprocal of this is just 1 over the magnitude with negative 89.9. So again, we'll notice that the impedance is very small. This does not seem to impede a very high frequency signal or current. So again, if we have a current of 10 cos 377t passing through this circuit, if that is my impedance, then the voltage across the circuit is very small, 0.03537 phase negative 89.9. Essentially, this is lagging behind by 90 degrees. And so therefore my voltage is very small. Again, this should also be intuitive because capacitors are essentially short circuits for high frequency signals. And so essentially the current can just pass right through the alternating current can pass right through the capacitor. Now, there's a really cool effect here going on. Notice that if we have a number of circuit elements, we can calculate the impedance. The impedance ends up being a complex number. Well, a resistor determines the real part. A capacitor determines an inductor determines a positive imaginary part. A capacitor determines a negative imaginary part. So this essentially tells you that any linear circuit consisting of only inductors, capacitors, and resistors can be replaced by a single resistor and a single capacitor in series, or a single resistor and a single inductor in series, depending on the sign of the imaginary part. Or at the same time, they can be represented by an inductor and a resistor in parallel, or an inductor and a capacitor in parallel, again depending on the sign of the imaginary part. However, as long as we're dealing with, you remember from any resistors, any circuit of resistors can be simplified to a single resistor. Well, if we're dealing with alternating current, any circuit of inductors, capacitors, and resistors can be simplified into something containing only a resistor and either an inductor or a capacitor. So a few final observations. The techniques that we've discussed here do not work if the frequencies of the different sinusoids differ. I've used 377 as my angular frequency a lot. This is actually a very deliberate choice. In North America, we have 60 hertz. Well, 60 times 2 pi to get the angular frequency is 376.99 and change. Well, approximating 2 pi times 60 with 377 has a relative error of 0.026%. Very nice approximation. European power, on the other hand, is at 50 hertz. If it's at 50 hertz, the angular frequency is 100 pi, which is 314 and change. Now, mathematicians may note that it's odd that we're mixing radians and degrees. However, there is a justification for this. Well, recall that our phase shifts are 180 degrees or less, or pi radians or less. Now you have to ask yourself, I know what 120 degrees looks like. Is it really obvious that 2.094 or 2 pi over 3 is 120 degrees, how quickly, you can very quickly tell that 45 degrees is that. On the other hand, remembering that 45 degrees is 0.785 radians, it's a little bit more difficult. Also, is it entirely obvious that 2.094 and 0.524 are orthogonal? They differ by 45 degrees. Even if we were to add multiples of pi in there, it would not be obvious that these two are orthogonal. Finally, three-phase power requires roots of unity, and these are even worse if we want to write them with radians. They're very easy to write in terms of degrees. So in summary, we've discussed sums of sinusoidal functions. We've seen how the trigonometry is exceptionally annoying, and we saw that instead we can associate every single sinusoid, as long as the frequency remains the same, angular frequency, by nu phase phi, where nu is the amplitude and phi is the phase shift. Therefore, we can transform a sum of trigonometric functions into a problem of summing complex numbers. Once we've summed those complex numbers, we can transform back to a unique sinusoid. We explained why this is true using complex exponentials, and then we described phasor multiplication and phasor inverses, and then we saw how we could use phasors to solve simple linear circuits. So, I'd like to thank Dr. Niren for his assistance in answering questions, and Hua Qiang Chen, who noticed a few errors in my slides. Remember to contribute to WEEF, the Waterloo Engineering Endowment Fund, and hopefully you have a little bit better understanding as to what phasors do. Thank you very much for your time. Have a good day.